Alright, so we did this. This is the exact stuff that the students saw. You did this. You didn't do that part, but you did this. These are the exact same instructions.
Can you go back to the one that we didn't do?
So this is linked with the idea of classification. How do you classify organisms? And so this was a small activity where students... Did you do that?
Yeah.
So most people sort of reflexively do it. Which ones look alike? And so there's some different ways of categorizing it, right? If you were going to do that. Some people would do it... There's two. This one, there's two cards that have two stamps on each, right? So that would be one way to do it. But that's not at all what you guys ended up with as the racers that were on sort of the closest paths, right? The two with the two stamps ended up being pretty divergent. Is that a correct assessment?
Ours were in the center.
Yours were in the center?
I mean, they follow two different paths.
Right.
But so, in fact, this actually gets at a really cool point, which is to say, if you have people organize them into groups, and you haven't established what the goal is,
right,
you can establish all these different kinds of groups that tell you all kinds of interesting different goals about the nature of it, which is, what's the most immediate path to get out? Those are the 2s, whereas the 5s are...
That's a whole other set of interesting questions, definitely.
Right.
Yeah. Anything else?
I hope you don't mind their interrupting.
No.
This means it's great stuff.
It means that I don't have to talk as much. Always a good thing. So here are some of the student trees. They're a little neater than some of yours, but they basically show the same sort of information. And part of that is because there's only a certain number of different divergent events that you can come up with these 8 taxa or 8 groups, however you want to think about it. What I thought was really interesting is there's all these different styles of doing this, right? And then you guys added a few more. This one starts at the bottom, and they have lots of branches. And these guys really wanted to use their cards to organize it. It starts from the bottom. This one starts from the bottom. This one starts from the top and goes down. The reason I'm focusing on that is because that ends up being a big issue in interpreting more traditional evolutionary trees, is which way does time flow and how are people interpreting that. And I have this idea that perhaps geology students might have an advantage over some other people because we tend to be trained to think about time starting at the bottom of the diagram and moving up. However, from a small survey of what students did immediately upon this activity, they didn't conform to that in any more pattern than anyone else might. So here's somebody who's drawn a cladogram before. They used an expert-like way of making all the top bits line up that pretty much no one else did. Not important in terms of displaying their understanding, but important in terms perhaps of knowing that they have done this before. So what did we do? This is kind of a little crazy looking. We did this invention activity. Then we went directly to focusing sort of in a more formal way than I did with you guys on, if we look at these visualizations, here's some that look a little bit like yours, and how do we make that analogy directly to these evolutionary trees? So that sort of goes in this direction. So that's what they did in lecture. What they did in lab is they started out with this idea of an analogy to family trees. Most of us have some experience of seeing a family tree, and there's actually a lot you can glean from that. And there's a lovely paper by this guy Gregory, who it's basically a chapter on how to read evolutionary trees, and then another one, how not to read them. And in working through that, it's meant to be an educational sort of thing for people to read. And so I followed that line of reasoning from sort of starting with that family tree analogy and working towards some more abstract and then applied sort of paleo and biology examples. So this is sort of where we went from the student trees, and they were asked to take a look at this, and they compared it in their groups to, did we show that same pattern of branching, did we not? What you notice is, let's see, what's different here? This guy is rotated this way compared to that one. Does that make sense? If you took this spot right here, and you just rotated it like this, you should have done with this. Turns out there's a few different ways you can do that. It doesn't change the meaning of the branching, but it can make things slightly more confusing to look at. So, one thing that Noah was saying is their two racers with the two squares on, or the two patterns on each, ended up in the middle. That doesn't really mean anything in terms of if we're going to use this as an analogy to the relationships between the different ones. Where they are along the top doesn't matter. You can rotate and flip things, and it's just people's preference on how they're drawing it. What matters is how does that branch, what's the next branch it connects to? Does that sort of make some sense? Okay. So that was one of the instructor's comments. This is mine at the bottom. It says the typology is the same, and that's just the way we say it. Is that really a different cladogram or a different tree, or is the topology the same? So the next thing that the instructor did is basically work through some of the terms and the major concepts that we wanted to teach students that has to go with this. So here we go. Imagining the cladogram, a branching diagram of relationships between taxa. She put some letters at the top, make it easier to describe than triangle, circle, square, dash, something like that. So in Clado speak, I guess you could say, we would call these guys share a common ancestor. We would call them sister taxa, or sister groups to each other. They're their closest common relationships to each other. So like your sister would be in your family. Okay. Again, some of the other terminology that comes along with this. The node we talked about representing the common ancestor. It's where the branching points go.
Do you have students generate terms for important parts like that?
We don't.
It's fascinating.
It would be. What would be the advantage of doing
Yeah,
that?
I was going to write down the question, and I just,
No,
I
it's okay.
I have to dart out of here.
Go ahead and ask.
Late as I got here. Because sometimes I think for them to have to abstract it away from the interaction that they're having allows them to objectify it in a way that you need them to.
They have to sort of see it as an
embrace
entity.
These psycho words you're about to I mean, for me, this is why I struggled with biology. It's so nice to see. She's throwing words at me so fast, I definitely am not going to even try.
Right.
And so, like, that gives them an opportunity to go like, talk taxa, ours is blim blam, you know. And so I found it to work extraordinarily well in classes where they embrace the scientific term rather than reject it because
they already have a name for it.
They've got a name, and they sometimes continue as a class to call it the name that they made, or they'll use the biology name. But either way, they've abstracted it and objectified the notion already. Can be helpful.
That's a very interesting
You could
point.
try it and see.
Yeah, definitely. You know. So I guess we are trying to find some balance between what has traditionally been done, which is basically, here's a tree, here's all the terms you need to know, here's the main terms, which is just like, no way, that's not helpful at all. So let's start with something where they're figuring out some of the essential reasoning. And then they've already, I mean, most of you guys in your discussions too talked about the branching points and what that meant or didn't mean or what it could mean. And so to try to build from that, okay, that branching point that we talked about, the name you might hear at some point is such. So I think there's like 3 terms on here. And I wasn't all that keen on having them do this, but, you know, it's a compromise, right?
Well, so, they have to leave with the scientific language.
I guess it wasn't clear to me that was the case, because they were immediately going to go to this family tree analogy to then work further.
Hopefully move some of these terms into the family tree.
That was one of the goals. Yeah, definitely. All right, so I don't really want to go through everything that we did with students. I want to kind of move a little further. Of course, I didn't know what all these transitions were. Yeah, so here's some more terms, which are kind of annoying. So we were talking about the fact that the things that branched towards the end of the race were more closely related. They had things that none of the other racers had, basically, and so that's That's what we mean, this term synapomorphine. It's really annoying. But if you ever hear people talking about it, and oh, okay, that's the thing that only a few organisms had, and not everyone had it, so that tells me about the relationship, that those things are closely related because they have it and no one else does. Okay.
Lots of words.
Moving
That
on.
makes
No!
my heart beat so fast.
Ah, we don't want that to happen. So one of the things I wanted to share is that there's these. I hate this convention. This is the bane of my existence the last few weeks because I find it extremely misleading, and I have this. I don't know. I have a really hard time because it doesn't seem to be. It's hard to imagine for me that flopping things over, rotating things on those nodes, and having it mean the same thing. It really does, but I want to make more out of the fact that A has this long branch, and that D has this little leafy branch. And to some extent, that's always going to be the case because that is represented there, but these other conventions make a little more sense to me. I think this is sort of like Steve's group here. So those are all conventions that are used.
The other thing I've run into with the bane of your existence is I've heard students refer to it as therefore D must be the common ancestor of all of them.
Yep.
Because that looks like a long straight line to them, so therefore that must be the same organism existing along the whole. Which
there's all sorts of crazy reasoning you can get yourself into. All right, so I don't want to go too far.
Go back. So you're saying that a student sees a line that goes all the way from the origin to D, so it must be the same thing.
It must be the same thing, right?
Got it. Right. Yeah.
They can't perceive that where it looks like just as a fork coming off. They can't perceive that's actually a.
You could swap D and E, and it would mean exactly the same thing because all you're worried about is the last branch, right?
It is.
But it visually seems to pull your eye that direction.
Oh yeah, you're right.
So like I can deal better with E and D over there on the top right one personally. When I'm drawing these, if I'm just trying to draw a sketch, I have to do one like that before I can draw one like that. So if I'm having that problem, I'm not really an expert. I'm sort of in between what I would consider expert, but compared to students,
what's the
I'm an expert.
justification again of the model, the conventional model?
Don't know. I spent all day yesterday trying to find that out, and I don't
The model
know.
is often the justification. We have a lot of those in physics.
Do you?
That's the way it's done.
That's the way it's done.
And what's the difference between the second and the third? Except that the lines
Curvy.
got bolder.
Curvy.
Smooth average,
I don't know.
dude.
That was one I didn't understand why that they put the second and the third.
Right. I mean, the fourth one has a little bit of a hint of forward motion at the vertex.
Yeah.
Right. Rather than something funny about the sidewaysness of the split, whereas moving forward, I don't know.
Funny.
That must be part of what's bugging me about that too.